So welcome to this talk on numerical gymnastics, an introduction to optimal control. Now let me start with a little anecdote that explains the title. So when I was at school, I was good at math but rather bad at sports, and people would say, can't you calculate how you've got to move? And in a nutshell, this is what we are going to do. Now, superficially, I think the art of moving in an elegant way and math have absolutely nothing to do with each other. One requires talent, and the other, well, requires another sort of talent, but once you get to calculating, it just requires, processor power. Could processor power ever be a substitute for the talent that's needed to move in an elegant way? And if that's not the case, then it's obviously bad news for robots, because then they would have to move in this stereotypical robot-like way forever. And the good message is that to some extent you can actually replace that talent by numerics. Thus the title, Numerical Gymnastics. To give you a short outline, first we'll discuss the ever important question of why. Then I'm going to give an overview over the theory that is needed. And we discuss two large fields. First, linear systems. In linear systems, we can actually get analytical solutions. We can certainly write down a control law that will make the system do what we want. And then for nonlinear systems, we're going to have to use numerics. So let's start with the introduction. If you consider a traditional industrial robot, like this CNC mill here, or a larger industrial robot, and generally the idea is that these systems have full control over their dynamics. So they have strong motors, and they have one motor for every degree of freedom. And this means that they can essentially follow any trajectory they want to follow. And of course for a mill that's rather important, because the trajectories decide how this thing you're producing gets cut. So of course, the motors still aren't infinitely large, so you have torque and velocity limits for the motors. But unless you go totally crazy with your path, they are more or less secondary. And the result of all this is that the intrinsic dynamics of the system don't matter. So when we write a program, G-code or something, that runs on this mill, then we don't really have to know how much the portal weighs, or if there's any crosstalk between the axes. We just tell it to go from there to there, and it does it. Now let's look at another industrial robot and compare it with a biped. And the thing I want to point out, actually these screws here. And the screws are there for a reason, because they keep the base of the robot attached to the rather large iron plate beneath it. And again, the screws are there so that the robot doesn't need to worry about reaction forces. The base can essentially take any force the robot puts on it. And again, this industrial robot can move however it wants to. And the bipedal robot doesn't have that luxury, because the leg that's on the ground is really only pushed to the ground, and it's not bolted to the ground. And so this bipedal robot really has to worry about not to overdo or not to let the reaction forces on the stance leg get too large. And this problem can't be solved by stronger motors alone. If I stand like this and then I try to put my body on this side, then I'm going to fall over, no matter how strong I am. So for more fancy robots, like this bipedal robot, the intrinsic dynamics really do matter. That is what I just said. The result is then that no longer we can have any trajectory. We need to choose the trajectories carefully. We need them to still do what we want, but we are restricted by the intrinsic dynamics of the system. Now, of course, bipedal robots are somewhat hard, and starting with them is probably not advisable. So we need some more simple toy system. And a toy system that's discussed a lot is this Acrobot. What you see here is that it has, by the way, do we have a laser pointer or something? No, okay. Never mind. So what we see here at the top, it has just a bearing, and in the middle it has a motor. And it's two pendula essentially attached to each other. Now, of course, this is completely academic. You could just add another motor or put the motor to the top and makes the second bearing rigid. But it demonstrates the techniques nicely. And one important feature of the system is that it is what is called under-actuated. So we have 2 degrees of freedom, two angles for the two links, but only one actuator input, this motor. And the techniques I'm going to show you will let you deal with this kind of system and solve the problems you want to solve. So what do we want to do? Now, first of all, we want to understand how this thing moves, because this is now going to be important. We want to know what actually happens when the motor puts some torque in the system. Then the next task we might wish to do is to assume that it is already at the top. Now, if it was at the top, so inverted from what's shown here, then it's obviously unstable. The slightest disturbance will make it fall over. And can we get it to actually balance at the top so that it moves the motor in such a way that it drives out small disturbances? And this is what's going to be the topic of the first part. This is what we will call linear systems. And then the last and most complicated exercise is to actually make it swing up from the bottom. That's where we need numerical techniques, and that's the second part. So now the rest, or the next slides are going to be rather technical, so I can only invite you to ask if there's something that's unclear. I still try to give you an intuitive view, but there are going to be some equations. So let's start with analytical mechanics. And the central equation in analytical mechanics, of course, is Newton's second axiom. We know that. And it's usually stated as F equals m times a. Now, of course, you also know that acceleration is the second derivative of position. So we could write it as x dot dot, where x dot dot is the physicist's way of denoting the second derivative, is equal to 1 over m times f. And in usual situations, f will depend on the position. I've shown you a usual example on the right side. So this is a point mass on a spring. And of course, the force, if it's below this point marked 0 here, then we assume that the spring pulls it up. And if it's above the point marked 0, then gravity will pull it down. So the force on the mass will depend on the position. And thus we get an equation of the form that the second derivative of the position is equal to 1 over the mass times some function of the position. In this case, it's just a linear function. And of course, if we have more than one mass, then we get this variant shown below, where there are several accelerations, and the forces in general will depend on a function of all the positions. So, for example, if you have 2 point masses linked by a spring, then it's clear. And actually, for rigid bodies that are not point-like, you get something similar, which is called Euler's equations, but we won't care about that. Now, there's one important kind of motion that we have to consider, and that's constrained motions. And the canonical example is a single-link pendulum, like shown here. And the constraint then is that the string that ties the point mass to the fixed point above remains taut. And then from Pythagoras you get that x squared plus y squared must equal L squared at all times. And this complicates the equations of motion, because in addition to the trivial force due to gravity, Fg, we now get a constraint force that actually makes the string pulls on the point mass in such a way that the string always remains taut. And now in this simple example, of course, it's relatively easy to get an expression for this Fc. But in more complicated examples, like the acrobot, it is going to get rather difficult. And the solution for this type of problem that's usually employed is called generalized coordinates. And what we do is just choose an angle phi, like here, and then we have x equals to L sine phi and y equal to L cosine phi. And, well, of course, sine squared plus cosine squared is 1. So then the constraint is automatically fulfilled for any possible reason, for any possible value of phi. And then we don't have to worry about the constraint anymore. But of course that comes at a price, and the price is that we now need to think about what the equations of motion for phi are. And the answer to that question again is called the Lagrangian mechanics. I won't go into detail here, but essentially that's the cookbook recipes that you can just follow. So you need to write down the kinetic energy as a function of the generalized coordinates, and the potential energy as a function of the generalized coordinates. And then you get an equation and you have to calculate some derivatives, and finally you get the equations of motion. I could show you an example, but it's just large. It's not hard, but it's getting large quickly. So I'm just going to show you the result for the pendulum, which you could obviously get by other means. For the pendulum we get this kind of equation of motion. And I've also added a friction term. Well, it's clear, it's just slows this thing down when it moves. Now the same approach works for the acrobot. And we get two generalized coordinates, these two angles between the rigid frame and the first link, and then the angle between the two links. And again, the equations of motions now have that phi 1 dot dot and phi 2 dot dot are some function of the angles and the angular velocities. Again, I don't write this down. You can look this up in a number of places. It's rather large, but it's not complicated in the sense you can easily look it up and then have your computer solve it. It's just that it doesn't make much sense to put it on a slide. So what we now have to do is to actually solve these equations of motion. And just another quick reminder about differential equations, because that's what these things are. Now, as you know, the solution to an ordinary equation would be a number. And for a differential equation, the solution is a function. To give you an example of a differential equation, we have dx to the t equal to square root 1 minus x squared. This is an example of a differential equation of first order, and it's also explicit because the highest order derivative stands alone on the left. Yeah, and as I already said, physicists like to abbreviate the first time derivative by x dot and then the second time derivative by x dot dot. So how do we solve this? Well, we could note that if you take sine and the derivative is cosine, and again, by the squaring theorem, we can rewrite the squaring theorem to show that this function x of t equals sine t actually solves the differential equation. What's more important is that it does that for any value for this alpha here. That's a general feature. In general, we don't get a function as a solution, we get a family of functions. And to determine a concrete value for xt at a given time t, we need this alpha, and we usually determine it by what's called initial conditions. So if we know x at time 0, we can determine alpha, then we can get a number for any x of t. And the combination of an ordinary differential equation and initial conditions is called an initial value problem. Now let's get back to where we actually want to be. We want to solve this pendulum equation. It's still explicit because the highest order derivative is on the left, but it's second order. There's a second order derivative. What do we do about that? The usual trick is to introduce a dummy variable, in this case called omega of t, and consider a system of first order equations, like in the second gray box. And we have omega dot equals minus gamma omega minus k sine phi, and phi dot equals omega. There's a typo here, sorry. Now you can see that if you find two functions, omega of t and phi of t, that fulfill this system, then the resulting phi of t will also solve the original equation. And so this works similarly if you have systems of second order equations and so on. So we only ever need to worry about systems of first order differential equations, like here. And we just write them as vectors. So instead of writing the two equations above, we write x and it's a vector. An important point is that we now need n additional conditions. For the pendulum, we need phi of 0 and omega of 0. So we need a starting position and a starting velocity. So, yeah, okay.
Sorry to interrupt. Just
Yeah.
Can you come back this slide just before that?
Where?
This slide before this one.
Ah, yeah, of course.
What is V exactly here?
That's a typo.
Oh,
It's
right.
meant to be omega.
So it should be omega. Okay, good. Sorry.
So, a special case is actually a linear system where you get x dot, that's a vector again, equals ax, and A is a matrix. And we assume, well, if this matrix is independent of x, t, and t, then there's an analytical solution. And in a nonlinear case, you can just solve it via numerical methods. And of course, there's a variety of systems that will do that for you. I guess the most commonly used numerical method is called the Runge-Kutta method. And there are many implementations like GSL, the GNU Scientific Library, if you like C, or Octave, if you want a scripting language for that kind of thing. And you provide some function to calculate this f of xt, and the software calculates xt at chosen points in time. And I guess I could quickly show you how that looks like. If that works. So this is what I just said. So you provide some function that will calculate f of x and t, and the computer just solves this equation for you. So you can get results. And of course you know how it looks like. Well, that's a pendulum, it's damped. There's not much to see here. More interesting is probably the Acrobot. Now that's the Acrobot. And that's a free Acrobot actually, so we don't have any control input yet. We assume that there are two links and they're both not driven by any motors. And as you may know, that this is then a double pendulum and it's chaotic. And you nicely see that it is indeed fairly irregular in its motion. Now for later use, there's also a program that will just show this visually. Again, this is how the motion of the free Acrobat would look like. Now the task is, I mean, like this will never get to the top, of course. It's already clear from energy arguments. The task is now to drive the link in the middle such that it stops this irregular moving and just gets to the top. This is what we want to do. But first we stay at the linear part. So we consider this differential equation again and let x be a two-dimensional vector for now. A concrete example is the equation for the pendulum we just saw. Now let's plot this f of f of x. And let's have concrete values, k equal 1, gamma equal 0.2. Now how do we plot a function that goes from two-dimensional vectors to another two-dimensional vector? And the idea is to make a plot like this, where you have at the positions small arrows that point in the direction that this function points to. Now the nice thing about this plot is that it gives you a graphical intuition of how the solution of this initial value problem would look like. Because you start somewhere and then you follow the flow. So assume we place the pendulum at the beginning of this blue curve, so just at some distance from this, just drive it from the base position, and then it just goes like this. And because it's damped, it spirals into the point 0, 0, which is just the pendulum hanging down. And if you start it even further away, then it goes over once, and then it spirals in to the next stable fixed point. Now that's it. The next thing is then, of course, a point in phase space where its function is 0 is called a fixed point. And it's called a fixed point because if it is a fixed point, and then the time derivative at this point is 0 and it never changes. So if we start at a fixed point, we stay there for all time. The interesting question is what happens if we start near a fixed point. Turns out that I have two. The microphone is empty, first of all. Does anyone know what to do?
Take the other one.
Okay. Yes, I can go on without the microphone. Dieses hier, ist das an? Is this working? Ah ja, okay. So, continue sitting. Why not? So there are two important cases of fixed points. One, the stable fixed point, where small perturbations die down, or we have unstable fixed points where small perturbations grow. This is again shown in this slide. Exactly. So the stable fixed point obviously corresponds to the pendulum hanging down. And then if we go a little bit away from the stable fixed point, it just returns, as shown in the blue curve. And the unstable fixed point corresponds to the pendulum pointing up. Now, if it were exactly in that position, it would indeed stay there forever. But the smallest deviation from that will just grow, and it will rapidly leave the unstable fixed point. And what we can now try to do is to understand the behavior of the system in the vicinity of a fixed point. And we do this via a method called linearization. And the idea is that near the fixed point, the system is actually almost linear, because these terms are small if x is near to x0. And f of x0 is obviously 0 if it's a fixed point. So then, near the fixed point, the system is described as a linear differential equation. If we actually take as a new variable the distance to the fixed point. Yeah. Now, how does the solution to a linear differential equation look like? Well, we know that if we have x dot equals ax, then the solution is x of t is x0 times e to the at. And there are two important cases. If a is greater than 0, then this explodes. And if a is smaller than 0, then it dies down. So now, of course, we don't have this in one dimension, but we have it in more than one dimension. So again, to analyze the behavior of our fixed points, we need to derive a similar criterion for more than one dimension. Now, first, the solution of the linear differential equation in n-dimensional systems, it just looks very much the same, except that x is now the matrix exponential. And the important criterion that we are after is decided by the eigenvalues of this matrix A. So if the real part of all the eigenvalues is smaller than 0, then the exponential of A times t goes to 0 as time goes to infinity. This means that we have a stable fixed point. So if the linearization around a fixed point has a matrix where the real parts of all the eigenvalues are smaller than 0, then we have a stable fixed point. And otherwise, in general, it blows up. Otherwise, in general, it goes to infinity. And we can do that for the pendulum, and the equations of motion give rise to these derivatives. And we have the two fixed points. Again, this is the one where the pendulum is hanging down, and this is the one where the pendulum is pointing up. And unsurprisingly, the stable one has eigenvalues with negative real part, and the unstable fixed point has one eigenvalue with a positive real part. So finally, we can get to the actual mission of trying to balance this thing. Now we'll try to balance it near the top, of course, at phi equals pi and omega equals 0. Now if we succeed, we will always stay near this fixed point. And therefore, thanks to linearization, we are effectively dealing with a linear system. Because if we always stay near the fixed point, then the approximation of the system by linear methods will always remain good. So if we know how to do optimal control for a linear system, then we can actually solve this kind of balancing problems. We can solve it for the pendulum, and later we'll be able to solve it for other systems too. Now to control the pendulum, first of all, we need control input. And if you look at the equation again, we just add some term u that we can control. It's equivalent to a torque or a force acting on this mass, which we can steer. So we can push this mass here, or we can push it to the other side. And the idea is to choose this force such that after a small disturbance, we actually manage to return to the fixed point. Now, in general, a linear system with control will look like this, and the task will be to drive it to x equals 0. Remember that the new variable is not is now actually distance to the fixed point, as I said earlier. So the task is to drive it to x equals 0. Now, so if we start with this original equation and we linearize it around the unstable fixed point, we end up with this. And it has the form shown above. And actually offer an intuitive picture of that. In the phase space, I already showed you this follow the flow type of equation, of situation. And well, if you have a free system, then essentially we throw a piece of wood into the water and it just follows the flow. On the other hand, if you have a controlled system, then we have some control over where we go. But the important thing is that we don't have full control. We can't go wherever we want. And also we somehow have to conserve our effort. So we have to oppose the flow as little as possible. Now, to solve this kind of problem, we introduce the so-called optimal cost to go, and it's also called the navigation function. Now, essentially, eventually we will want that on the phase space, but we start with the discrete version, and it's possibly best explained by trying to solve this maze. And how do you solve a maze like this? From a given point, you just solve it. You find the optimal way out. Now, of course, you can solve it from a few other points as well. Now, there's an important feature of all these optimal paths, namely that once they meet, they never diverge again. And that's obviously clear, because if you are at some point, then the shortest path to the exit won't depend on how you got to the point in the first place. And this suggests that we don't actually need to draw these paths. We can just draw these little arrows. What these little arrows give us is the first step on the optimal path to the exit from that point. Then we take that step, we end up in a new point, there's a new arrow that tells us the first step from the optimal path to the exit from that point. And of course it's the same as the second step in our original path. So this field of arrows solves the maze completely. If you want to get out, we just follow the arrows and we get to the exit. So here's a complete solution of the maze for every point. Now the question is, can we encode that information even more efficiently? It turns out that we can, because it's already sufficient to know the distance, the optimal distance to the exit, like this. Now how do you use that? Well, you just start somewhere and then you move in such a way that the distance always decreases. For example, if you're at this junction and you come from here, you could either go here and go from 19 to 18, or you could go to here and go from 19 to 20. Now, if you want to actually leave the maze, then you have to go the direction where it decreases. And this is what the cost to go is. So once we know the optimal cost to go, we've actually solved this kind of problem. And similarly, if we can introduce this cost to go on the phase space, we've actually solved our control problem. And now we have to think about what kind of equation this cost to go will fulfill. Now, let's assume we are in some place and then we have a set of actions. If we remain at this maze example, for example, if we are here, we could go up, right, or down. So the set of actions for this place are these three. Then we introduce the state transition equation. For example, if we start here at 5, 8, and we go right, then we end up in 6, 8. And we have to introduce the cost for one step. And for this discrete example, it's just going to be 1, but it's going to get more complicated later. Now the type of, G star is the optimal cost to go. And what type of equation will it have to fulfill? Well, suppose we consider that point X. Now, if the optimal cost, from this point X, we could go up and then have 14 further steps to go to the goal. Or we could go right and have 14 further steps to go to the goal. Or we could go down and have 12 further steps to go to the goal. Now, if that's supposed to be the optimal cost to go, then it better be 13. So it has to be the minimum of all possible actions, of the cost of taking that step, plus the optimal cost to go from where we end up. Now, in particular, of course, if we know the optimal cost to go, G star, then that gives us the optimal action, and it's just the minimum of all possible actions of that function. And again, intuitively, this should be relatively clear. The optimal cost to go from some point X to the goal has to be the cost for the optimal first step, and then the optimal cost to go from that place where we end up to the goal. And we also introduce the optimal policy, which we denote by pi star. Now we need to take this discrete version and turn it into something continuous. And So exactly. For the first step, we take the discrete version and rewrite it. Now this g of x doesn't depend on the action, so we can take it inside the minimum. We replace this x prime by the transition equation. And then we end up with this equation still discrete, and this motivates that the continuous equation might look like this. Now, of course, for infinitesimal steps, so for steps that are potentially very small, then the step cost will be almost zero, so that makes no sense any longer. and we need this normalized step cost, L of x and u. And this equation is called the Hamilton-Jacobi-Bellman equation. And that's the central equation for the type of problem. So in a maze, it was easier. I mean, taking one step has a cost of 1, maybe. But we now need to worry about the cost of path and phase space. And what we essentially want to minimize is, one, the distance we stray away from the goal and the control effort. And we achieve this by having a path cost that might look like this. So we integrate over the entire path the distance to the goal and the control effort. And this gives us the cost of a certain path. And then we can derive the optimal cost to go. It shows us for the optimal path what this cost is going to be. And you can get even more general and replace this squared by quadratic forms. Essentially, it's the same thing. It's just that if you have a function that solves this type of problem, then you can get even more general. But you could just take this thing that we had in the last slide. There are two important things, though. One thing is that this term must never get smaller than 0. So you can't have a place where you can linger and accumulate negative cost, because then the problem is no longer well defined. You could just go to the place where you have negative cost and then stay there forever, and this would then be unbounded. So this matrix Q would have to be non-negative definite, and similarly, control effort always has to cost something. So this term has to be strictly positive. Now again, if you have a linear system described by this type of equation, now let's assume that the cost to go, which is now a function on the phase space, would be described by a quadratic form like this. And the idea is that we assume that, then we can use this Hamilton-Jacobi-Bellman equation to show that this matrix S, which parameterizes the cost to go, has to fulfill an equation like this. That's obviously very useful, because if you look at this equation, then essentially A and B are the matrices that define how our system looks like. Q and R are the matrices that parameterize our cost. So the only thing that's unknown is S. So if you look at the coefficients of S, then this is really a quadratic equation in the unknowns. So it's a system of quadratic equations. And as such, it's not really surprising that we can solve this and get the matrix S relatively easily. But if we have the matrix S, then we have really solved the problem, because then we have the cost to go, and from the cost to go we can get our optimal action. Yeah, and we get the optimal policy, and what's possibly interesting is that the optimal policy is just some linear function in our position. So we have to know where we are, and we calculate a linear function, and we know what to do. Now if we put in some numbers, we can use the computer to calculate S. This is just our pendulum equation from earlier, and we get this kind of optimal policy. So let's look how this looks like. Now on the left here is the phase space. Again, we have the distance in omega, so that's, and distance in phi. And well, we start somewhere, and you just move to our fixed point along this trajectory, which happens to be optimal. And what's shown here in the background is the optimal cost to go. Now if you look at this over time, here's time, and again we got the distances in position and in angular velocity. You show that it nicely takes you from a rather large deviation to the goal. Remember that 0 corresponds to the pendulum pointing upwards. This really works. Now, of course, this is not particularly interesting. It wouldn't really make sense to introduce this framework if this was the only kind of problem we can solve, because a PD regulator can do this just as well. What's more interesting is that it also works for underactuated systems, such as the Acrobot. And let me just show you this plot. Oh, great. Yeah. So the mouse will not work, but never mind. Okay. So again, you see, this is actually the future of the Acrobot. It needs to take really large excursions to get back. So what I can't show you because the mouse doesn't really work. This doesn't start at 0, obviously, otherwise it would just remain at 0. So it starts a little bit off 0, but then it goes back. So even for the Acrobot, we can now balance at the top. Although we can only do this for fairly small disturbances, but we can do it. And we can do it despite the fact that we only have one actuator to deal with 2 degrees of freedom. This is probably fairly significant. And the nice thing is that this also works in real physical systems. And here's a system that implements just this technique. And it also has 2 degrees of freedom. It once has this angle.
Can you do it on 0?
Oh, yeah. This also has 2 degrees of freedom. Why? Well, the first degree of freedom is clear, it's this one. And the second degree of freedom is the position that it moves on the table. Now, why do we need that second degree of freedom? If you just try to solve this as a PD controller or something, and it was like this. Now, how do you correct a deviation like this when you accelerate? And then it's like this. But it has no reason to ever slow down again, because now this angle is 0, so why should it slow down? So if you did this with a simple PD type of controller, it just drive into the wall, on the one side or on the other side. That's no good. So what we need is to have 2 degrees, to consider 2 degrees of freedom, and have it actually return, after it balances this out, it has to return to the starting position, or at least approximately. And that's that.
The principle of Segway.
Yeah, the Segway is a bit different because it still has a person on top. I don't think a Segway could drive completely autonomously like this, because the person will also do something. I think I heard that the Segway is just a PD controller, but I'm not sure. I mean, the original Segway, I probably don't know. I think you can actually build a Segway as a PD controller and have the person on top do the rest. But here you need, this is actually A2R. Of course, there are many details. For example, estimating this angle is not really easy. You need to combine several sensors. But the thing that balances this is the A2R controller I just showed you. And it's really derived in an analytic way. So we measure the position of the center of gravity and the mass of this thing and the moment of inertia. Then we get the equations of motion, and then we get the control parameters that essentially work. Okay? That's good. So now, of course, there's a swing up task remaining. And we have to solve this numerically. And the technique, which I'm going to tell you something about, is called direct collocation. And as all numerical techniques, it's based on discretization. So what we do is we take this function u of t. Remember, that's our control input. Now, of course, at first, this is infinite dimensional. It's a function. At any time, you can do anything you want. And then after discretization, it becomes finitely many numbers ut. We call this a control tape. Why not? Now, once we have that control input, we can put the control input into the equations of motion, and we get a path. Now, from that path and from the control input, we can again calculate the path cost. And this is what we want to optimize. So we now have a finite dimensional optimization problem in these finitely many numbers. And what we want to optimize is this sort of function. Now this could, for example, look just like a path cost I introduced for the linear systems. It could also be something different. It doesn't really matter. Now, how do we solve these equations of motion inside the optimization software? We do this by discretizing x of t as well. So not only do we have discrete variables ut that parameterize the control input, we also have additional variables that parameterize this position of the system in phase space. And we can get constraints. So it turns into a constraint optimization problem, and the constraints will have to make sure that the system follows the equations of motion, that it starts at the chosen start point and it ends off a goal. What do these constraints look like? For example, if you take a third order polynomial, we can get these coefficients in terms of the values and the derivatives of the polynomial at 0 and 1. And this also then relates the value and the derivative of a polynomial at position 1/2, so between 0 and 1, to the values at the start and the end of the interval. Now, if you apply this type of equation on one time interval, then you can use this to enforce constraints that are essentially equivalent to differential equations inside this interval. And the last thing we do, is that we introduce yet another discretized function, which is w of t. Now the function itself will be the integral of the path cost. We discretize it. Now, of course, this also fulfills the differential equation. You could just differentiate that, and then you get w dot of t equals that without the integral. Then you do the trick from the last slide, and you get some constraints for your w. And in the end, your optimization variable is very simple because you just optimize the last wt. So the objective in your optimization problem is very simple, but you got a lot of constraints. And the nice thing is that we can solve this kind of problem relatively efficiently, and there's software to do that. Again, this is the problem just stated in general. You have to minimize some function subject to constraints. And one kind of software you might use is called the interior point optimizer IPOpt, which is available on the internet. And now if you do all this, then you can actually get a swing up trajectory for your acrobot. It looks rather nice. It looks like this. and it manages to swing up the EchoBot. And it takes about a minute to calculate. So it's not really fast, but it's still fast enough. And it scales relatively well with dimension. Now there's one last problem, and we are done. Because one thing we lack is feedback, right? I mean, we've calculated our u of t. We calculated that beforehand. So while we run this, we can't really react. If anything happens, if there's a small disturbance, then we are bound to fail because we don't get this disturbance under control. We just do what we calculated earlier. So this cannot work. I can show you how it's not working. So that you can appreciate the solution later. What? It's really annoying that the mouse doesn't work. Sorry about that. Oh, okay, sorry. No, sorry. No. Guess I don't get that fast enough. Sorry. So now it has an awful number of colors. Let's switch some of them off. So what we have here is first of all, well, Q0 and Q1 are just the two angles. And in red and orange, you see the trajectory that we want to follow. Again, we choose our coordinates such that the goal is at 0, 0. So the nominal trajectory ends at the goal. That's nice. The bad thing is that the actual trajectory, if you disturb it just slightly, doesn't end at the goal at all. It does something completely different. So at first, it looks as if it's actually almost on the trajectory we want to follow, but then it diverges. And of course, that's clear because we have small disturbances and they grow because they're not controlled. We don't have feedback. So direct collocation is only one part of the answer. We still need feedback. We can't go completely with open loop control. And now even more mathematics. The next idea is that we linearize again. We can't any longer linearize around a point. We now have to linearize around a nominal trajectory. And the good message is that we can still do that. Now again, we introduce new coordinates, these error coordinates, that just measure how much we deviate from our nominal trajectory. And then we can derive a linear system for the behavior of these error coordinates. And this is the thing we really want, because this linear system might allow us to get an analytical solution and get something that we can implement online to have feedback. Of course, it's not quite as good because we now have these matrices A and B. And for the balancing problem, they would be constant because we were linearizing around a point. But now we are linearizing around a trajectory. So these matrices are time dependent. The good thing is that it still works. I guess I said that. But the matrix S, and remember that this was the parametrization for our cost to go, it's now a solution to a differential equation that looks a lot like the equation we had before, just that there are now lots of time-dependent terms. We also get an optimal action. Now, we don't have to solve that online either. We can calculate this S of t for various times. We can calculate the optimal action. And which we call this product of matrices we call K. What we get here is that the optimal action is U0 of t. This is what we calculated by direct collocation, minus K of t, which is a matrix which we can also calculate offline, times the deviation from the nominal trajectory. And well, kt is just some gain, like the gains we had before, but it's time varying. Now this is very nice because we can do all the expensive stuff offline. We can find the nominal trajectory offline, and we can calculate time-dependent gains. And all we need to do online is to measure the deviation from the nominal trajectory and apply this correction. So really, all we have to do online is carry out this product, and that's very cheap. And finally, I can modify this program to put back in what I just took out, compile it again, run it again, and who would have guessed? The nominal trajectory and the actual trajectory, even though they start off from slightly different positions, now actually converge. So this would allow us to take a real acrobot and drive it from the bottom to the top.
So you have to predict a corrective action for every disturbance, for every time.
No, that's a nice thing. I don't have to predict anything. I just have to make sure that the disturbances never grow too large. Right. So I calculate offline this S of t, but it has nothing to do with, it's just one matrix. It's the same matrix always. Okay. And I measure my disturbance, and I just multiply this. So the last part, the multiplication between this matrix, which I calculated earlier, and the disturbances, this happens online. So I don't need to know how the disturbance will look. I just need to hope for that it will be small. If it's large, then I'm dead. Then I can't do anything. But as long as it remains small, and if this works, it will remain small, then the scheme works. And I guess the conclusion is simple. Because if you recall the motion of the acrobot, that's really quite an elegant solution. We never told the computer anything about that. It would have to pump up the energy to get to the top. The computer figured that out itself using only numerics. So we can synthesize elegant and efficient motions using pure mathematics, albeit only for two-dimensional systems. But this method generally scales relatively nicely, even to higher dimensions. So I thank you for your attention. Yeah.
When you
Works again.
Perfect, thanks. When you apply this to a real-life scenario, what are the difficulties to get the motor, for example, running at the right velocities and changing directions when you need it? Are there some physical implications that were not spoken of here?
Yes, of course. So your motor will always have finite bandwidth. So the motor can't change direction. The motor can't change direction infinitely fast. Now, if your system is slow, then it doesn't matter much. If you look at this physical system here again, you see this this seemingly useless thing at the top. That's to make it slow. So it won't matter as much that these motors don't react infinitely fast. If your system is slow enough, then your finite motor bandwidth is just an additional source of noise. And it's small, and so it gets dealt with using these techniques, because that's what they do, deal with small noise. But eventually this has to break down. Eventually your motor is so slow compared to what it needs to be that you die. Further questions? Guess that's not the case, so thanks again, and see you at the party.